Hi. In this mini lecture, I want to talk about properties and definitions of continuous functions, specifically how sequential continuity relates to epsilon delta continuity. So in the lecture on Wednesday, we presented a theorem that a function f is continuous if and only if one of two properties holds. So one is the definition in the class. For every epsilon, there exists a delta such that once y is close enough to x, then the distance of fx to fy will be less than epsilon. And it doesn't really matter whether you have less than or equal to or strict inequalities here. This is a matter of choice. I like less strict inequalities here, non-strict inequalities, because it's often just you don't have to worry less in the proofs, but it's a matter of choice. What matters is that these epsilons and deltas are strictly positive. Otherwise, it doesn't make sense. Now, another property of continuity that you've seen in 131a, and that is related closely to the first, is that if you have a sequence, for any sequence of points that converges, so for all xn and all limits, and limit is unique, but we have to state that there exists such a limit, then the limit of the function values also converges. So in this lecture, I will prove that 1 implies 2 and 2 implies 1. One of these is easy and the other one is harder. So proof that 1 implies 2. This is the easy direction. It's easy because you can do a direct proof. So let's set things up. We are proving 2. Assume that 1 holds. And I've written it up there, so I won't repeat it. We have to still choose epsilon and delta. We have to choose epsilon that we apply it to and the point that we apply it to. Now we want to prove 2, so let's set things up for it. We are proving for every sequence in x, so let xn be a sequence of points in x that converges to x in x, that is limit as n goes to infinity of xn is equal to x. Okay, we want to now get this into a more appropriate form. So what does this mean? This, and anticipating that we want to bring distances here somehow. So and we want to bring distances, and we want to prove convergence here. So let's fix an epsilon positive and define, just so that we are clear about what our sequence is on the y end and what our sequence is on the x side. Yn is equal to f of xn and y is equal to f of x. We want to show that yn is equal to y. So epsilon is now fixed. We want to make yn close enough to y. Well, to do that, we need that xn is close enough to x, and where that comes from is the convergence. So there exists a capital N. Well, first of all, we have to know how close things need to be. Well, by 1, there exists a delta positive so that if distance x to y is less than delta, then distance fx to y, let's use a different fx to z because we are already using y, to fz is at most epsilon. Okay, so this is already quite nice, but now we have the sequence xn. We have to ensure that this holds. Since limit as n goes to infinity, xn is equal to x, there exists a capital N so that if n is bigger than or equal to capital N, distance xz, x to xn, is less than delta. And you could clarify that with this choice of delta. and applying convergence, we find an n such that this is true. Now, okay, so this is all in the setup and using definitions. Now, we want to prove that yn converges to y, so use this same n, and let's prove everything works. So if now n is bigger than or equal to n, then distance x to xn is less than delta, then by choice of delta and the continuity here, we get that distance of f of x and f of xn is less than or equal to epsilon, but this is the same thing as distance of y and yn is less than or equal to epsilon. So what we just said is that for the epsilon that we gave, there exists an n such that if n is bigger than or equal to n, then y has distance less than or equal to epsilon to it. And this is the same thing as limit n goes to infinity of yn is equal to y. And this is exactly what we wanted to show. So it's mostly a proof where you have to be careful about the quantifiers. Okay, now 2 implies 1. And this is the harder proof. And this is a proof, it's harder because the only simple way to do, the only reasonable way to do this is by contradiction. You could also structure it as contrapositive, but contradiction in this case is easiest. So assume 2, that is, if you have limit n goes to infinity xn is equal to x, then limit n goes to infinity of f of xn is equal to f of x. Now we want to prove 1. That is epsilon delta continuity. That we want to prove that this holds, but by contradiction, assume also that 1 fails. That is, and now you have to think carefully what it means for 1 to fail. That means that there exists an x in x, and we fix that. And so that for every, so that there exists an epsilon for every quantifier turns into an existence quantifier, such that no matter the delta, there exists a y such that the distance from x to y is at most delta, but this is how an implication fails, and it's crucial that this is a but. So this holds, but also distance fx to fy is bigger than or equal to epsilon. So there are very close points where the distance is bigger than some given threshold epsilon. Well, we have to construct some sort of bad sequence from this because we want to contradict 2. So this holds for every delta, and this is a common thing. If it holds for every delta, we apply it to give a sequence by doing the following trick. So if we use delta equals 1 over n for n in natural numbers, there exists a y, which we now call x and n, such that distance from x to xn is less than delta. So there, for every delta choosing such, we can find an xn like that and choose one of them. But distance fx to fxn is bigger than or equal to epsilon. And delta here is 1 over n. Okay, so we have our sequence whose distance is going to 0. So now distance xn is between 1 over n, and it's always positive. So by squeeze theorem, limit as n goes to infinity of distance x to xn is equal to 0, which is the same thing by definition as limit n goes to infinity of xn is equal to x. So we have a sequence that converges to x. But well, now what we have, so then by 2, limit as n goes to infinity of f of xn converges to f of x. But this starts already to contradict the fact that we have that these should be faraway points. But let's write it out more clearly. So there exists an n such that if n is bigger than or equal to capital N, distance of f of xn to f of x is, say, less than or equal to epsilon over 2. But above, we got, by construction, that distance of fxn fx is bigger than or equal to epsilon for all n, in particular for all n bigger than or equal to n. So these two are contradictory, less than or equal to epsilon, bigger than or equal to epsilon. So these two together lead to a contradiction. The same number cannot be both less than or equal to epsilon over 2 and bigger than or equal to epsilon. And one might say because epsilon is positive. If epsilon were 0, of course, this would be possible. And this concludes this proof. Now, for any statement that you have, you should have some sort of application, either a practical one or a theoretical one. So here is a small application of this theorem and how to use it in practice. Suppose x is complete. F is a continuous function. If we have a Cauchy sequence in x, then the image sequence is also Cauchy. So Cauchy sequences are mapped to Cauchy sequences onto continuous maps as long as the domain is complete. Well, let's combine these. So xn is Cauchy and x is complete. So there exists an x such that limit as n goes to infinity of xn is equal to x. Now, by continuity, and what we just proved, limit n goes to infinity of f of xn is equal to f of x. So f of xn is convergent. And because it is convergent, it is Cauchy. So f of xn is equal to yn is Cauchy, and we're done. So this is a convenient short proof that once we've established this sequential continuity being equivalent to epsilon delta, we can immediately prove these things. And we can pass convergence from the domain to convergence in the target space. That concludes this lecture.